Our planet is extraordinary. It provides everything life needs. Trillions of creatures, plants, and us.
Well, you look down at the Earth from space, and everything that we know of that's life is down there on that planet, that beautiful planet that you now are going around every hour and a half. And that's almost overwhelming, just the beauty of the Earth.
It's unique in our solar system, but is it unique in the universe?
It's important for us to understand the conditions that led to the formation of the Earth, because then we can look for those conditions around other stars, and if we find those conditions there, then that would suggest that other Earths could be forming elsewhere in the universe.
Could there be other planets like ours among the stars? To find out, we must travel back in time and discover how the Earth was made. Rewind the clock 4.5 billion years, and this is what you see. This speck of dust will become the Earth. By combining with countless others. They're all part of a giant cloud called a stellar nursery. The first step of planetary formation is about to start. An event that will transform the cloud into thousands of infant solar systems, including our own. The same process is happening today, 7,000 light years away, in the Eagle Nebula. Our own solar system formed inside clouds of gas and dust like these.
There are these three trunks of gas, and they're nicknamed the pillars of creation. And they're trillions of miles long. These are huge structures.
The clouds look dense, but they're actually very sparse.
These gas clouds are incredibly tenuous. You'd have to compress basically a mountain's volume worth of this stuff, squeeze it down just to make a little tiny rock like this.
To compress the gas and dust into dense stars and planets takes a supremely powerful event. One that can only follow the death of a giant star. In 2007, the Spitzer Space Telescope captured this image. A ball of hot gas behind the Eagle Nebula. Evidence that a huge star has exploded and sent a vast wall of gas racing toward the pillars.
There's a wave of hot material approaching the pillars of creation, and this may be a shock wave from a supernova, a dying star.
Supernovas briefly outshine entire galaxies. Superheated plasma blasts into space at 70 million miles per hour. A mighty shock wave speeds toward the pillars of creation. When it hits, it will demolish them. It will also create new worlds. Supernova shock waves smash into the pillars, compressing the thin gas and dust into dense clumps. Each is a new star, a new solar system.
molecular cloud minding its own business gets blasted by a supernova explosion, crushing the cloud down into stars and planets.
Wind back 4.5 billion years, and our solar system starts the same way. A supernova crushes a massive, dusty cloud into a protoplanetary disk. A thin, nebulous cloud becomes a dense whirlpool of gas and dust. A solar system in the making. One star is destroyed. A new star is born. Our sun and its planets. This is the first link in the long and unlikely chain of events that made our world. For Earth to even be here, we had to beat astronomical odds.
A host of different factors have to line up to get a planet just like the Earth. You have to have the right distance, the right size, the right kind of moon.
On Earth, all the conditions are just right for life.
To get a world like ours, you need a lot of aces. Somehow, our solar system hit the jackpot. But the big question is, did it happen anywhere else?
One of the universe's most violent events triggered the birth of our planet. A sparse cloud crushed into a dense swirl of dust. Some of this dust will become planet Earth. But how do tiny dust grains create entire worlds? A supernova explosion triggers a chain of events that will eventually create the Earth. The formation of our solar system. A hot ball of gas grows in the center. This will become our sun. The dust that swirls around it will form the planets. But first, the grains must stick together.
So we have this interesting conundrum, right? So this disk consists of gas and dust particles. They're about the size of, let's say, particles in smoke, right? Let's say cigarette smoke, right? So these are small things. And somehow we have to get from those little grains to what we see on the Earth.
Gravity is a powerful attractive force. It shapes galaxies and solar systems. But specks of dust are far too small to pull on each other. Somehow, they clump together to form planets. So if gravity doesn't bind them, what does? In Germany, scientists are on the case.
Okay.
They can simulate how dust behaves in space inside a huge tower.
Here we do free fall experiments. So the whole experimental setup, including our dust aggregates, are in perfect free fall. It is simulation of space, but a very good one indeed. I think this is the closest you can get to space on Earth.
Researchers place dust in a container and load it into a launch capsule. At the base of the tower, they lower it into a super powerful catapult. This launches the half-ton capsule from 0 to over 100 miles per hour in a quarter of a second. 400 feet up, the capsule reaches the top of the tower, then plunges back down. A drum of polystyrene balls 30 feet deep breaks its fall. All this gives just 10 seconds of zero gravity, just enough time They hope for the dust to stick.
3, 2, 1, and go.
Moments after the capsule launches, the dust inside becomes weightless. The grains clump together, just like the early solar system. These images reveal how dust particles came together 4.5 billion years ago to form the Earth.
The force that binds the aggregates together is not gravity. They are too small for gravity to be efficient. We think the force that binds the aggregates together is electrostatic force.
It's the same reason that when you pull your clothes out of the dryer, you know how the clothes sometimes stick to you? That's the same effect that allows one dust particle to stick to another.
Dust particles join to form balls of fluff.
The little static charges that they have can make them stick when they hit. And you get something sort of like the dust bunnies that I have a lot of underneath my bed.
These cosmic dust bunnies are planets in the making. They start out smaller than a pinhead, then grow. The dust is now in clumps, but it's still just balls of dust. Turning dust balls into rocks takes a whole new process. A cosmic electric storm. Space clouds build up charge just like clouds here on Earth, generating huge bolts of lightning.
Balls of dust can turn into solid rocks by an energetic event like lightning.
The electric bolts smash through the dust balls and heat them to 3,000 degrees Fahrenheit. In minutes, they cool and fuse into solid rock. Meteorites today still carry these ancient rock balls inside them. These tiny globules were once the building blocks of planets. To form the Earth, these tiny balls must collide, stick, and grow.
Rocks begin to build up by accidental collisions, which can take a long time.
Eventually, the protoplanets, as we call them, the baby planets, get the size of asteroids, kilometers across.
The baby Earth is now the size of a few city blocks, big enough for a new force to take charge: gravity.
At that point, a single asteroid will gravitationally attract a neighboring asteroid. And so those two asteroids that would have passed in the night are gravitationally attracted and they hit each other.
Once gravity starts to rear its head, things really speed up because instead of just randomly plowing through material and getting bigger that way, now it's starting to draw material in.
Gravity pulls rocks together, then holds them there to produce bigger and bigger piles of rubble.
So this formation process, which was taking a long time to get to the size where gravity kicks in, suddenly gets kicked into overdrive, and the planet grows very rapidly.
But planets are more than just overgrown rock piles. These rocks are lumpy and inert. How did the Earth become round and full of life? The early solar system is a construction site for planets. Dust sticks together to form rocks. Rocks join to form asteroids. But most asteroids look nothing like Earth.
And when you look look at a close-up of an asteroid, it looks like some kind of distorted peanut, like a potato that's been sort of bashed. You can see giant craters and oblong shapes.
The young Earth is one of billions of misshapen space boulders. To become a planet, it must first become round. That process only starts when it's several hundred miles across, when its own internal gravity begins to change its shape.
Once you get enough material, enough mass, the gravitational force becomes stronger. Any giant mountain will be crushed down by the force of gravity.
The gravity is so strong that can actually break rocks, and the rocks itself can act like a fluid, making an object round.
Huge outcrops of rock crumble and fall. The immense self-gravity of the early Earth crushes it into the most efficient shape. A vast round ball of rock. A lopsided pile of rubble transformed into a miniature world. The Earth has a new shape, but it's still just a ball of rock. Its structure will also soon change. Cosmic rocks and boulders still rain down from space. Each collision heats the ground.
There's a huge amount of energy stored in an object that's moving rapidly, and when that hits the Earth, all that energy is dumped into the material, and that heats it up and melts it. And the Earth became molten and stayed that way for a long time.
The young planet is no longer solid rock. It's a seething, molten mass. Just like this blast furnace at the Severstall plant in Detroit.
Believe it or not, this process behind me makes life on Earth possible.
They feed in ground up iron ore, a mixture of rock and metal. Just like the early Earth. Put iron ore in a furnace, and the heat melts everything.
This molten iron is at 2,700 degrees Fahrenheit. That's about the temperature of the surface of the Earth 4.5 billion years ago. Imagine an entire planet molten. In the distance, you will see thundering volcanoes spewing out lava. It would be a scene right out of Dante's Inferno.
Iron is heavier than rock. Now molten, they separate.
This is amazing. We're witnessing a process which created the very crust of the Earth billions of years ago, the crust that we walk on every day.
Molten rock rises to the surface and cools to form the crust. Molten iron sinks underneath. Inside the Earth, it sank all the way to the planet's core. The rocky surface is where we live. But without Earth's molten iron core, none of us could survive.
This process separated the iron from the rocky minerals. As the iron descended to the center of the Earth, it eventually created a magnetic field, and that's why we're here today.
The molten iron swirls inside the Earth's core and generates a powerful magnetic field around the planet. A cosmic shield against deadly radiation from space. But the young Earth is still small. far smaller than the Moon today. This newly formed world must grow. It must also avoid being blown to pieces. Thousands of protoplanets are hurtling around the solar system, and some are heading straight for Earth. It's 100,000 years since our solar system formed. The young Earth already looks like a planet. It's round. It has an iron core and a rocky surface. Yet our baby planet is just a few hundred miles across. It has a long way to go. It must grow 4,000 times more massive. And it has competition. Thousands of other protoplanets shoot through the solar system, often colliding at over 20,000 miles per hour. You can find proof of this ancient destructive era in modern-day Arizona. Not Meteor Crater itself, that's just 50,000 years old, but the asteroid that gouged it out. That was 4.5 billion years old. Mark Sykes and Marvin Kilgore think the asteroid came from a violent event in the early solar system. The asteroid flew through space for billions of years. Then it hit Earth. They aimed to find a fragment of the asteroid, a remnant from the period of planetary formation.
About 6 miles from here is Meteor Crater, and that was an impact 50,000 years or so ago, and it spewed a bunch of pieces out.
They're convinced the original asteroid was rich in iron, so they've come prepared with some impressive metal detectors.
Does it work?
Oh, yeah.
That's the sound we're listening for.
But even with a quad-drawn metal detector, meteorites are hard to find.
Yeah, are you pretty convinced there's nothing there?
I don't really, not detecting anything.
They find metal, but no meteorites.
My great discovery of the afternoon has been this bolt and this piece of wire.
It takes hours of searching and many false alarms. Then, with the light fading, the detector sounds again.
How about that? Success at last.
This meteorite is over 90% iron and nickel. It could only form right in the core of a protoplanet. The protoplanet it came from must have smashed apart in a brutal collision.
Well, in the early solar system, it was a pretty violent place, and these protoplanetary embryos would smash into each other, and they would shatter each other, exposing the interior cores like this. It was a very tumultuous time.
Entire worlds reduced to chunks of rock and metal and scattered into outer space. In the early solar system, these vast collisions are common. The young Earth is in danger. The period's name is the Titanomachian, literally, the War of the Titans. All rocky planets, the Earth included, go through this destructive phase. Sometimes they shatter completely. Sometimes one consumes the other.
All the big guys are sort of competing with one another in a very violent way, actually, to see who comes out on top by eating all their neighbors.
The battle lasts over 30 million years. Finally, thousands of protoplanets have combined into a few full-size planets. Mercury, Venus, Earth, Mars, and a fifth planet, Theia. It's racing toward Earth, our planet's last giant impact. Theia is the size of Mars, big enough to destroy the Earth.
If that thing had hit us straight on, it could have literally blown the Earth to bits, and then we wouldn't even have a planet today.
If this Mars-like object had a direct hit with the Earth, perhaps there would have been another asteroid belt where the Earth is today.
But Earth is in luck. Instead of a head-on crash, Theia strikes a glancing blow. It's the most violent event the Earth has ever known. The impact turns the Earth back to a molten world. A vast magma ocean 600 miles deep. The Earth barely survives. And the encounter changes our world forever. Material blasts out into space. Enough rock to build a mountain as wide as America and 10,000 miles high.
It would have been so much energy, so much catastrophe. Huge amounts of material blasted off and went into orbit around the Earth.
The debris forms a huge ring around the Earth. This gathers together to form two rocky bodies, both orbiting the Earth.
Something the size of Mars hit the Earth about 4 billion years ago. Lots of material would have been thrown off. We now think that it may have formed not only one moon, but two.
For millions of years, two moons dominate the Earth's sky. Eventually, they drift together and collide. Two moons merge into one. The massive moon we see today.
There's no other planet that we know of that has a moon as large as ours in comparison to the size of the planet. We're almost a binary planet, two worlds going around each other.
Without this large moon, we might not even be here.
The moon plays a key role in the survival of life here on the Earth. And the reason is that the moon in its orbit stabilizes the Earth.
The moon keeps the Earth spinning at the same angle. That steadies our climate.
The fact that the Earth's axis stays in the same direction as it goes around the sun produces the seasons, but regular seasons, things that life can depend upon as it evolves.
Earth is neither too hot nor too cold for life, thanks to our distance from the sun and our massive moon. The Earth is not covered in ice or steam, but in liquid water. Yet that water must come from somewhere. The newly formed Earth is dry. To get water, our planet must once again face disaster. It's 500 million years since the sun first ignited. 4 billion years from now, the first humans will set foot on Earth. The moon has just formed, and the Earth is a desert.
One of the more amazing ideas in astronomy is that the Earth started out hot and dry. There was no water here originally.
As the planets formed, the sun's intense radiation vaporized the water in the inner solar system. Farther from the sun, temperatures were cooler. So in the outer solar system, ice and water collected on comets and asteroids. While closer to the sun, the young Earth was dry.
So things changed. What happened? How is it that now we have this wonderful water cycle? Well, the water probably came from somewhere else.
If you want to have a solar system that has a lot of water in it, you have to bring it from the outer parts down into the inner parts. And you can do that through comets and asteroids.
Comets and icy asteroids contain huge reserves of water. But they're hundreds of millions of miles from the young Earth. Then, something changes. An event that tosses the asteroids and comets right across the solar system. Jupiter, Saturn, Neptune, Uranus take a cosmic roller coaster ride.
So this isn't an event that happened when the solar system was young. Think of it as more of its teenage breakout years where they just started to party for a while.
The young planets have not yet settled into stable orbits. As their orbits shift, Jupiter and Saturn fall into an intricate dance. Every time Saturn orbits the Sun once, Jupiter orbits twice. So they always line up at the same spot. Each time, gravity tugs them in the same direction. First, they destabilize each other, and then the entire solar system.
The whole thing just goes kaplooey. The analogy I like to use is when a bowling ball hits pins, it just goes bam all over the place. That's what this would have looked like.
Planetary pandemonium. Neptune and Uranus switch places. Saturn races outwards. The giant planets scatter billions of asteroids and comets onto new paths. Many head for Earth.
These asteroids and comets would have been scattered all over the place, right? Some of them hitting the Earth and Moon.
Cosmic missiles bombard the Earth.
We believe that every square inch of the Earth got hit by a comet or an asteroid during this period. It would not have been a fun time to be here.
The bombardment lasts hundreds of millions of years. Until finally, the gas planets settle into the stable orbits we see today, restoring order. But Earth itself has fundamentally changed. Those comets and asteroids were not just made of rock, but of ice, frozen water.
Comets, we know, are made out of ice. They're dirty snowballs in outer space, and even asteroids can bring water and ice to the Earth.
Our oceans are full, thanks to the cosmic hailstorm.
So, next time you're drinking a glass of water, realize that you're probably drinking comet and asteroid juice.
The arrival of water is the final step to create a habitable planet. A sequence of catastrophes has created a world that's perfect for life. But has it happened elsewhere among the stars? Or are we alone? How did we get here? Planet Earth only exists because of a chain of extraordinary events. A lucky throw of cosmic dice.
5 billion years ago, the odds would have seemed extremely slim that a planet like Earth would form in a rather unremarkable arm in the Milky Way galaxy. It's like trying to throw 2 6s, but with dice that have thousands of sides.
We know it happened once, else we wouldn't be here. But what are the odds it happened elsewhere? That other planets have life. Life like ours needs a planet with the right temperature and size, a stabilizing moon, a protective magnetic field, and just the right amount of water. The conditions must be perfect. Yet amazingly, there may be countless Earth-like planets out there waiting to be found. Thanks to the sheer scale of the universe. We may find one any day now with the Kepler Space Telescope. Jeff Marcy is mission co-investigator.
It has only one goal, and that's to discover Earth-sized planets around other stars that you see in the night sky.
Earth-sized planets are hard to spot. Before Kepler, astronomers took 20 years to discover around 500 planets. Most were gas giants hundreds of times bigger than Earth. Since Kepler, that number has exploded.
Kepler has already discovered a couple thousand planet candidates. Many of them are members of multi-planet systems, 2, 3, 4, 5, and even 6 planets, all orbiting the same star. So we're finding an absolute avalanche of planets out there among the stars.
Kepler has found one planet only twice the size of Earth and the right temperature for life. We don't know yet if this planet has other Earth-like attributes, like liquid water. But even if it doesn't, there are many more planets out there. Kepler has found only a tiny fraction of them because it only looks at a small part of the sky.
It's not even looking at the whole sky. It's looking at a very tiny slice of stars in the galaxy. And in fact, if you were to look up, you could cover it with just your thumb.
In the whole of our galaxy, there are 200 billion stars. Many will have planets.
Based on our knowledge from Kepler and other searches, something like half of those stars, perhaps even more, harbor planets.
That means at least 100 billion planets have formed in the Milky Way. Earth-like worlds may be rare, but it seems a safe bet they're out there somewhere.
So the odds of getting an Earth-like planet are extremely small, much smaller than getting a double 6 at craps. But if you have a lot of dice, you're guaranteed to get 6s.
And if you have a lot of planets, you're guaranteed to get Earths. There are so many planets in our galaxy. Even if the chances are 1 in a million, there should be thousands of Earth-like worlds.
Our universe at large has hundreds of billions of galaxies, each of which is more or less like our Milky Way. So the number of planets in our universe is virtually uncountable.
Alien Earths must be everywhere.
Now, we haven't discovered even one of them yet, but statistically speaking, it is a rock-solid certainty. There are millions of billions of planets like the Earth out there.
And with that many Earth-like planets, surely some of them will have intelligent life.
I would bet everything, I would bet my house, that there is another Earth out there somewhere.
Planet Earth, a jewel in the darkness of space. Our home is timeless, beautiful, and incredibly violent. Volcanoes are one of the most powerful natural phenomena on the planet. They create new land, destroy the old. They blast out gases that transform the air we breathe. Deep in our oceans, volcanic heat fuels strange new life. Volcanoes help power the living Earth. Now we search for signs of life on alien worlds. We know life needs water. We know it needs energy. And that's where volcanoes come in. They pump out vast amounts of energy. Find volcanoes on other worlds, and we might find life. The search starts here. The planet orbiting closest to Earth, Venus, a world that appears very much like ours.
Venus and Earth are roughly the same mass, they're roughly the same distance away from the sun, so they're kind of like twins.
$3 billion years ago, Earth and Venus were very similar. New land, new oceans, an atmosphere. Both planets were perfect for life. But on Venus, something went wrong.
Something made Venus diverge radically from the history of the Earth.
Venus took a definite turn to the dark side a long time ago.
Venus is a hellhole, our evil twin.
Today, Venus's surface is like a furnace.
It's 900 degrees Fahrenheit on the surface, and it's hot enough to melt actually some metals, so you wouldn't stand a chance.
Venus is a greenhouse world. Its atmosphere is thick with carbon dioxide. It traps heat from the sun like a blanket. These actual images of Venus's surface reveal a barren, superheated wasteland. Venus's thick blanket of CO2 killed the planet. The CO2 came from volcanoes. Orbiting space probes gave the first clues. Radar punched through Venus's thick clouds and revealed volcanic formations across the planet. like formations we also see right here on Earth. The shield volcanoes of Hawaii. Shield volcanoes get their name from their round, flat shape. These volcanoes ooze, but they ooze for thousands of years.
Once we were able to map the entire surface of Venus using cloud-penetrating radar, we started to study the landforms there, and we saw a lot that was actually very familiar. In particular, we saw giant shield volcanoes that are very similar to the shield volcanoes here in Hawaii.
The radar images of Venus were dead ringers for the shield volcanoes on Hawaii. Sometime in the past, Venus had volcanoes.
For the first time, we had a picture of Venus revealed. And boy, were we shocked. We found a scarred surface, a volcanic surface.
There are at least 1,000 volcanoes that are very large, and maybe tens or even hundreds of thousands of smaller ones.
3/4 of Venus's surface is lava plains, evidence of an ancient cataclysm. This could have been a home for life. Instead, it was engulfed by fire. Volcanoes belched trillions of tons of carbon dioxide into Venus's atmosphere. Temperatures soared. The seas boiled dry. A runaway greenhouse process began.
On Earth, carbon dioxide is able to absorb into the rocks, it's able to absorb into the ocean. But on Venus, you have no water, and it's now so hot that carbon dioxide can't even combine with the rocks. So as carbon dioxide was released into the atmosphere by volcanoes a long time ago, over time there was less and less of a method to take it back out of the atmosphere.
If Venus ever had life, volcanoes sterilize the entire world. Earth remains the only living world we know of. That may change. This is the gas giant Jupiter. Its moons frozen and dead. Or so we thought. Look closer, and a mystery emerges. A cloud hanging over a cold and lifeless world. On Venus, volcanoes turned an Earth-like world into a superheated hell. Finding volcanoes on an Earth-like world was no surprise. But spotting volcanoes on a moon was a shock. In March 1979, the Voyager 1 space probe gave us our first close-up view of Jupiter's tiny moon, Io. A world we once thought cold and dead.
And they saw something really weird. They saw this arc next to the moon. And it looked almost as if like there was another moon behind it.
And we scratched our heads and said, well, what could that be? Everybody knows that Io is dead, boring, uninteresting. And then people realized, oh my God, it's a volcanic eruption.
We found that it's covered with volcanoes. It is tremendously geologically active. There are volcanoes erupting all the time. And what they're erupting is a lot of sulfur, and it gets very hot. And sulfur, when it changes temperature, changes color. It can be red or orange or yellow or black. And so these pictures of the face of Io make it look like a pizza covered with different kinds of cheese and olives where the little black spots are.
Io is not dead. It's alive and kicking. It has over 400 active volcanoes. The largest, Pele, erupts from a gigantic lava lake. It reaches nearly 250 miles into space.
If we could stand on the edge of that lava lake and watch that plume shooting off into the blackness of space, that would be an incredible sight.
Pele's eruptions are so huge because Io is so small. There's nothing to hold the lava back, virtually no atmosphere, and very little gravity. These vast eruptions make Earth volcanoes look like firecrackers. How can such a tiny moon be so volcanic? The answer is Jupiter. Just as the moon raises tides in Earth's oceans, Jupiter raises tides on Io, tides of solid rock. Io's orbit around Jupiter is not a circle. Sometimes it's closer, sometimes farther away. Jupiter gives Io a gravitational pounding.
And so Jupiter's gravity pulls on it a little bit harder and a little bit weaker. And what happens is the moon stretches like this. It's called a tidal force, and it doesn't stretch this much, it's only a little bit. But in fact, it's enough to heat it up.
It's just friction. It's the same way when you rub your hands together really fast, they begin to feel warm. Friction creates heat.
Jupiter's gravity stretches and squeezes Io. In every 2-day orbit, the ground rises and falls by nearly 300 feet. This pummeling generates intense heat and gigantic pressure.
Wherever there's a weak part in the crust, the lava rushes out. So the volcanism is on a planetary scale. Unlike here on Earth, where there are certain bits that are active around the plates or in weak spots, this is an entire moon that's one active hotspot.
Thanks to the incredible power of gravity, Io is the most volcanically active world in the solar system.
The volcanism on Io taught us something new. It taught us that internal sources of energy can drive volcanism in a way that's different from that on Earth.
In outer space, tidal forces, the differential squeezing of the moons of a gas giant, can also create volcanic activity. That was a game changer.
Io is a lava world, superheated and violent. It's hard to imagine anything surviving there. Yet the volcanic principle here is the same as on Earth. Pressurized, superheated magma below the surface blasts through fissures in the crust. But not all volcanoes need magma. They don't even need to be hot. Travel out past Jupiter into the outer solar system, and it gets cold, really cold. The distant moon Triton is so cold that much of its tenuous atmosphere can freeze solid. Yet there are volcanoes here. Volcanoes that may hold the secret of alien life. We think of volcanoes as mountains of solid rock. Deep beneath, rock is so hot and pressurized that it bursts violently out as lava. But not all volcanoes work this way. There are volcanoes on other worlds that don't use molten rock at all. Right at the frontiers of the Sun's planetary system, Triton orbits the ice giant Neptune. 2.5 billion miles from the Sun, the temperature is a frigid 390 degrees below zero. When NASA's Voyager probe flew past, it revealed a world covered mostly with frozen nitrogen ice. But the probe found something else.
When Voyager flew by, it saw these black smudges, and all of the smudges were going in one direction, almost as if there was a wind blowing dark material, dust, in one direction.
Signs of activity on a world so cold it freezes nitrogen. Volcanoes at almost 400 degrees below zero. Forget molten rock. Triton spews out a mixture of nitrogen and moon dust.
And the geyser not only has liquid nitrogen, which is in a fluid form, but also sort of dusty stuff that's lighter, that can even go farther in the weak winds. So you have this wonderful sort of double plume of an icy area and then a darker smudgy area, basically made of dust, like moon dust.
Triton's surface is nitrogen ice. Underneath, there are lakes of liquid nitrogen. How? Scientists believe it's because nitrogen ice lets light in, but doesn't let heat out.
There's almost a bit of a greenhouse effect going on Triton, that there's a layer of nitrogen ice that's transparent. And just like a greenhouse here on Earth, when you have glass, light can pass through it, but then the heat is trapped by the glass.
The sun shines through the surface and warms the nitrogen beneath. Just a few degrees is all it takes to turn nitrogen ice into gas.
A temperature gradient, a change in that temperature, that's what's important. And that's enough to melt the nitrogen underneath the surface on Triton and have it burst through as a geyser.
This is a cryovolcano, so cold that the material it erupts would freeze water as hard as rock. The solar system is more active than we ever imagined. We have found weird eruptions on many planets and moons. But so far, the only world where volcanoes are linked to life is ours. Or so we thought. This is Europa. It orbits Jupiter nearly 500 million miles from the Sun, a frozen 2,000-mile wide rock-hard ball of ice. From a distance, its surface looks smooth. Up close, it's a different story. Jupiter's enormous gravity gives Europa a pounding, just like its neighbor Io. The surface heaves and flexes, creating ridges and deep crevices.
When we first got close-up images of Jupiter's moon Europa, they looked a little familiar. And it turns out it looks like ice flows that you see when you fly over the Arctic. And it turns out it's the same thing. Europa has a several-mile thick shell of ice on its surface. And beneath that is a global liquid ocean.
Magnetic readings suggest Europa has an ocean that's a staggering 60 miles deep. Jupiter's gravitational pounding heats the rocky core and melts the ice above.
It's not unreasonable to think that as the core is being stretched by tides and heated up, possibly even molten, there's some boundary between a hot core and a liquid water ocean.
On Earth, underwater eruptions are surrounded by life. The same could happen on Europa. Here, the darkness is total. The pressure, a crushing 2,000 Earth atmospheres. A brutal world, but perhaps a cradle for life.
If life got off the ground here on Earth, why not on Europa? All the ingredients are there: an energy source, volcanic activity, a universal solvent, liquid water, a rich hydrocarbon chemistry. We have this mixing bowl of ingredients that happened on the Earth 3.5 billion years ago, and we have similar conditions on Europa. So some people are saying, if it happened here, why not there?
Life on Europa would be hard, but not impossible. On Earth, there is life at every extreme. Searing heat, crushing pressure, total darkness. Alien life on Europa might look surprisingly similar.
If life exists under the ice cover of Europa, they would be aquatic, but without eyes, because there's no light to speak of. They would probably use sonar in order to make sense of their surroundings. Organisms that literally feed off the energy from the volcano.
On Europa, volcanoes could be the source of new life. It's even possible that Europa is normal, that this is how worlds with life generally are. Earth could be the exception.
Think of it, Europa could be a template for billions of moons out there that have liquid oceans on them. So all of a sudden, our horizons have expanded several billion times by looking at the moons of Jupiter. What a shock.
Our solar system alone has over 170 moons. Multiply that across the universe, and that's a lot of places where life might take hold. All it takes is liquid water and a source of energy. Potentially, volcanoes provide both. And they are everywhere. This is Saturn, twice as far from the Sun as Jupiter. Yet it too has volcanic moons. And just like Jupiter's Europa, these moons could harbor life. This is one of the strangest worlds in our solar system, Saturn. A ring system 600,000 miles wide, an amazing 62 moons, and one with a secret.
Enceladus is one of Saturn's smaller, more distant moons, and it's been known for a long time that it's covered in ice because it's very bright, very reflective. But when the Cassini spacecraft went there, it discovered something amazing.
The Cassini probe revealed something incredible, not on the planet itself, but on Enceladus. Backlit by the sun, a gigantic plume bursts out into space, a sure sign of volcanic activity. It was an amazing discovery, and it helped answer a question that has puzzled scientists for decades: the mystery of Saturn's E-ring. Saturn's outermost ring is vast, almost 200,000 miles across, and it shouldn't exist. The ice particles that make up most of the ring are too far from Saturn to stay in orbit. They constantly drift away into space. Something replenishes the ring: the ice volcanoes of Enceladus.
Those plumes that are ejected from Enceladus' south pole, it turns out that those are going into space, and they're not just going away. They're feeding a ring around Saturn, the E-ring. So this little moon is giving something back to its parent planet.
Water blasts from Enceladus's volcanoes, hits the vacuum of space, and instantly freezes into tiny ice crystals, creating the vast E-ring. One mystery solved. Another replaces it. What creates the volcanic plumes? Cassini's cameras zoom in on the moon's south pole and capture these huge chasms scarring the surface.
There are these wonderfully huge cracks at the south pole of Enceladus. And as Enceladus goes around Saturn, these cracks open and shut as the tides go by. Now, these cracks are huge. They're hundreds of miles long. And when they begin to open, you would have this big crevasse opening at maybe 100 miles an hour down the length of that. It'd be incredibly spectacular.
Huge gravitational forces crack the surface open and closed at enormous speeds. Like Europa and Io's orbits round Jupiter, Enceladus's orbit round Saturn is elliptical. This helps generate the heat to melt ice and create oceans of water beneath the surface.
The conditions of the water underneath Enceladus' surface are absolutely perfect for life. It's the right temperature, it'd be a good pressure for life. Liquid water would be just like seawater here on Earth. And the chemistry of the water we see shooting out of these vents suggests that it is very similar. There's salt, there's organic material in it as well. So we have identified a place in the solar system where there very well may be life right now.
Cassini has detected complex carbon molecules in the ice plumes. Combined with liquid water, these suggest that just maybe life could survive deep within this enigmatic moon. Enceladus may not be alone. Another of Saturn's moons might also harbor life. Titan, one of the largest moons in our solar system. The only moon with a thick atmosphere. A frozen world, ice as hard as rock, lakes of liquid methane. Yet here too, we might find evidence of volcanoes and the tantalizing prospect of alien life. A raging inferno on the surface of Io. Eruptions of ice and nitrogen on Triton. Volcanoes are one of the most destructive forces in our universe. But out of annihilation comes the possibility of life. Even here, on Saturn's mysterious moon, Titan. It's 3,000 miles across, larger than the planet Mercury. It's the only moon in our solar system with a thick atmosphere. There is weather here, storms, winds, rain, even lakes, all so cold that liquid methane takes the place of water. and it's loaded with chemicals that life needs to survive.
Titan has turned out to be absolutely one of the most interesting places in the solar system. It's an active world. It's the only moon with a thick atmosphere, an atmosphere very much like Earth because it's mostly nitrogen, and it turns out an atmosphere loaded with organic molecules.
Methane gas high in Titan's atmosphere reacts with sunlight and creates the kind of chemicals life depends on. But if sunlight converts methane into organics continuously, why doesn't the methane run out?
The atmosphere is full of methane, and yet we know methane is being destroyed by sunlight on a short time scale, so it shouldn't be there. There needs to be a source of methane.
Something on Titan pumps out a continuous supply of methane. Cassini has detected what looks like a crater. Its interior is as deep as the Grand Canyon. Infrared cameras reveal different types of materials surrounding the crater. Scientists believe the green areas could be volcanic, perhaps plains of lava ejected from Titan's interior. If it exists, lava, Titan style, is a super chilled, icy slush. But compared to the rest of Titan, even ice slush is scalding hot.
On Titan, the hot liquids spewing from volcanoes might be ammonia or water. Normally those are frozen solid on the surface, but if they're heated beneath the surface somehow, they could erupt out.
On Titan, what comes out of volcanoes is methane and ethane. And that's probably the reason why we have this very thick cloud cover, this orange haze around Titan. This haze probably came from outgassing from the volcanoes of Titan.
Even for volcanoes on a world as cold as Titan, you need heat. That's what turns ice into liquid and generates eruptions. On Titan, that heat has two sources. Radioactive materials warm the interior. And Saturn's huge gravity massages the moon, just like Enceladus. These two forces generate enough heat to turn ice into water and liquid methane to gas.
We think of volcanoes as being hot and ice is cold, and yet if you're out on Titan, where you're a billion miles from the sun and it's quite cold, then those flows of just barely above freezing water, ammonia, ice, they might be the hottest things around. So hot is a relative term depending on where in the solar system you are.
Could volcanoes on Titan give life a chance to survive here? Life as we know it needs an atmosphere, a solid surface, liquid water, and the heat to drive chemical reactions. On Titan, volcanoes could provide them all.
If you have a volcano on Titan, you'll have heat added to that. And all of a sudden you'll have liquid water surrounded by organic material. I mean, literally anything you need for the start of life.
If life does exist on Titan, it would be truly alien. It would breathe hydrogen in place of oxygen, perhaps swimming through lakes of liquid methane at 300 degrees below zero.
Perhaps there are oceans of ethane. Perhaps there are tide pools and perhaps volcanic activity and hydrothermal activity. Perhaps there are hot springs. Perhaps volcanic heat could generate enough to get life off the ground in Titan. That's a speculation, but it can't be ruled out.
But we may not need to travel this far to find signs of life. We may find it on a volcanic world much closer to home. The Red Planet, Mars, Volcanoes are everywhere, across the solar system. Worlds like Io, Titan, and Triton are complex, dynamic, and violent. Once, we thought that Earth was the only planet with volcanoes and with life. Now we find volcanoes everywhere, but we have yet to find alien life.
Volcanoes embody the sheer power of creation and destruction, and they go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either. In the cauldrons of volcanoes is the origin of life.
Volcanoes create new landscapes, seed the atmosphere with complex chemicals, replace the old with the new. If volcanoes are bound up with the processes of life, then where is the life on other worlds? Perhaps the answer originates in deep time when the solar system was young. On a young planet, much like our own. This is Mars. 3 billion years ago, it had active volcanoes. One still remains the largest volcano in the solar system. The cliffs leading to it are over 6 miles high. Mount Everest would sit comfortably in their shadow. And those are just the foothills. This is the awe-inspiring Olympus Mons. It covers an area the size of Arizona. Its crater alone is 53 miles wide. A Goliath like this takes millions of years to build, time that volcanoes here on Earth never get. On Earth, the crust is always moving. Deep below, a single hotspot pushes magma through the surface, building a new volcanic island. But while the hotspot stays still, the surface is moving. The new island moves away from the hotspot, and a new volcanic island takes its place. Mars is different. The crust is locked solid.
On Mars, there's just none of that tectonic activity. The crust is one big solid plate, and so if there's a hot spot, it just sits there and builds and builds and builds, and you get a bigger and bigger and bigger volcano. And that's why Olympus Mons is so huge.
Olympus Mons today is a frozen relic of a distant, warmer past. Mars's shrunken atmosphere means that Olympus now reaches almost into space. A true colossus, an extinct volcano on a dying world. But Mars's ancient volcanic terrain could, one day, harbor life again. The evidence is right here on Earth. On Hawaii, volcanoes have created mysterious tunnels called lava tubes. Channels left behind when torrents of molten rock surge into the sea. But some are now empty, and that offers us an opportunity.
Lava tubes are formed when you have an underground river of hot basaltic lava, 2,000 degree magma, molten rock. And picture it like a frozen river of water with the ice crust forming on the top. It's the same thing, only here the crust is solid rock, and the river keeps flowing underneath and makes this cave, this lava tube.
Extraordinary recent images suggest Mars's volcanoes also may have created lava tubes.
Any planet with basaltic volcanism, any rocky planet, will probably have lava tubes. And now we found a couple of them on Mars, in places where there are skylights, places where the roof has collapsed, and you can see from orbit right into those lava tubes.
If some tubes have collapsed, perhaps many others are still intact. The ancient relics of Mars's volcanic past. Now, after lying dormant for perhaps millions of years, these lava tubes could bring life back to the red planet. That life will be us.
One of the challenges of living on Mars for future humans will be the radiation environment, and in particular when there are solar storms, the cosmic rays coming in can be deadly, and having a storm shelter under some large mass of rock is really the best way to protect yourself from cosmic rays.
The tubes and caves of Mars's extinct volcanoes might one day make a perfect home, holding in air, shielding us from deadly radiation. A long-dead volcano could help fill a world with new life.
So when we look at this car, of course, all the atoms in this car came from stellar explosions, from supernova processes, and from stellar evolution. But they were created at different times during the evolution of the universe.
To understand how the universe made all the raw material we see here on Earth, we need to take an incredible journey and travel back through space and time to the moment our universe was born. In the beginning, there was nothing. No space, no time. And then there was light. Suddenly, a tiny speck of light appears. It was infinitely hot. Inside this tiny fireball was all of space. This was literally the beginning of time. The cosmic clock was ticking. Time could flow, and space expand.
At the earliest moments of the Big Bang, if you take it back to T=0, everything in our universe, everything we can see, all the matter and all the energy in all of the galaxies was once contained in a region smaller than the size of a single atom today.
The idea that our universe was once tiny originated from the brilliant work of American astronomer Edwin Hubble. Back in the 1920s, most astronomers believed that everything visible in the night sky were stars, and they were part of our galaxy, the Milky Way. But Hubble wasn't convinced. He studied a swirling cloud of light called the Andromeda Nebula and showed that it was a star city, another galaxy, far outside of our own galaxy. He showed that these other galaxies were speeding away from ours, and the further away they were, the faster they seemed to be moving. The universe was expanding. And if the universe was expanding, then at some point in the past, it must have been smaller, much smaller. And that it must have had a beginning. The idea of the Big Bang was born. Theoretical physicist David Spergel is a Big Bang expert.
The Big Bang theory is not really a theory of how the universe began. It's really a theory of how the universe evolved.
No one knows exactly what happened during the Big Bang, but scientists do know that a fraction of a second after the universe was born, this tiny, super hot fireball was already starting to expand.
We don't know how the universe began. So we start our story when the universe was a billionth of a billionth of a billionth of a billionth of a minute old. Pretty young. The universe was the size of a marble.
Less than a trillionth of a second after the Big Bang, the marble-sized universe was very unstable and underwent an enormous growth spurt.
During this period of incredibly rapid expansion, space itself was expanding faster than the speed of light.
In the same way that this hot glass ball inflates, so did the baby universe, expanding in all directions at once. And as it expanded, it cooled. A trillionth of a second after the Big Bang, the universe was small enough to fit inside the palm of your hand. A tiny fraction of a second later, it was the size of Mars. Another fraction of a second, and the baby universe had grown to 80 times the size of the Earth. A trillionth of a second after the Big Bang, and our newborn universe was still expanding, but it didn't contain matter. It was pure energy. Einstein's famous equation, E equals mc squared, showed that mass and energy are interchangeable. It gave us the knowledge to build weapons of mass destruction. It also revealed how the universe created the first matter. When a nuclear bomb explodes, a tiny amount of matter is annihilated and converted into energy. In the baby universe, the exact opposite happened. It converted pure energy into particles of matter. But there was a problem. The universe created both matter and its arch-rival antimatter, and when these two met, they obliterated each other. The infant universe was a war zone, a battle to the death between matter and antimatter. If they mutually annihilated each other, the universe would remain full of energy, with no galaxies, stars, planets, or life. Fortunately for us, there was an imbalance. For every 100 million antiparticles formed, there were 100,000,001 particles of matter.
But there was that one extra particle of matter left over in each volume. And that was enough to account for everything we see in the universe today.
This tiny imbalance led to all matter we see in the universe: galaxies, stars, planets, even convertibles, and ourselves. Astrophysicist Carlos Frank from Durham University in England explains.
We are a little bit of debris left over from the annihilation of matter and antimatter. We're the leftovers of that process. If the universe had not developed this slight asymmetry between matter and antimatter, the universe would have been completely boring. There would be no structure, there would be no galaxies, there would be no planets.
Quite what this newborn universe was like has challenged cosmologists since the Big Bang was first put forward. Now, in one of the biggest laboratories on Earth, they are able to recreate conditions that almost certainly existed an instant after the Big Bang. It's called the Relativistic Heavy Ion Collider, RHIC for short, and it's located at the Brookhaven National Laboratory on Long Island. It's like a time machine, taking us back to 10 millionths of a second after the Big Bang. Here, scientists like Todd Satogata accelerate subatomic particles close to the speed of light and then smash them into each other. The particles race around this 2.5-mile circular tunnel in opposite directions 78,000 times a second, and then collide inside this giant detector bigger than a 3-story house. When they smash into each other, they generate incredible heat, just like the real infant universe.
We believe the early universe was extremely hot, billions of times hotter than the center of the sun. And what you're doing when smashing these nuclei together is melting matter, creating matter hot enough to give us a glimpse of what the very early universe was like.
When the particles collide, they break open and throw out a shower of even smaller particles. It's a bit like discovering what cars are made of by watching them smash into each other.
You can race two cars together and smash them into each other head on. And when you do that multiple times, you start to see different patterns coming out. A tire comes out here, a radiator comes out there, and before long you can start to conclude that a race car is made up of these certain pieces.
What the scientists at Brookhaven have discovered is that within these superheated collisions, a completely new form of matter appears. And this matter contradicts the previous theories on the nature of the early universe. Because it's not a gas, it's a liquid. It was super hot, 100 million times hotter than the surface of the sun. There was so much energy inside the young universe that the particles vibrated so fast that it had no stickiness. There was no friction, and it flowed perfectly.
This liquid is perfect. It has no viscosity. In some sense, it would be the perfect motor oil, except it's 1 trillion degrees hot.
Inside the collider, this amazing liquid universe exists for only a tiny fraction of a second. The Brookhaven scientists have succeeded in recreating conditions that existed over 13 billion years ago. Despite the universe being a perfect liquid, it was in turmoil. It was full of subatomic particles smashing into each other, releasing more and more energy. There was so much energy that unless the particles slowed down, they would never bond and create atoms, the building blocks of matter. And the universe would never create the galaxies and stars, or even us. The universe is now 1/1,000,000th of a second old and has expanded from smaller than the size of an atom to 8 times the size of the solar system. After the incredible turmoil of the first millionth of a second, the universe was now relatively calm. Over the next 3 minutes, the expanding cosmos cooled sufficiently for protons and neutrons to bind together and form the first atomic nuclei, hydrogen and helium. These were not yet proper atoms. They were missing a vital ingredient, the electron. In the hot baby universe, there were plenty of electrons around, but there was still so much heat and energy, the electrons were moving too fast to form bonds. And it would stay that way for over 300,000 years. 380,000 years after the Big Bang, the universe had expanded to the size of the Milky Way. It had cooled from billions of degrees Fahrenheit to a few thousand. As it cooled, the electrons slowed down. The universe was now ready to make its first true elements. One of the scientists who discovered this critical moment in the story of the universe was Arno Penzias. 1963, 30-year-old Penzias and his 27-year-old colleague Robert Wilson began work on a new antenna in New Jersey. Initially, they were only studying cosmic radio waves, but they would stumble on one of the greatest discoveries of all time. As they started to test their equipment, they detected an unexpected background noise.
It was additional signal, and it appeared to be coming from the sky. We eliminated very carefully the ground, even the solar system, because we did this winter to summer, seasonal variation, man-made sources of equipment. All these things were eliminated.
In desperation, the two scientists began to wonder whether the strange signal might have another, more earthly origin. They found there were pigeons roosting in the antenna, and it was covered with droppings. They wondered if the pigeons were the source of the strange signal. There was only one solution. The droppings and the pigeons would have to go.
We finally got around to removing the pigeon droppings. We also had to remove the pigeons. That was a difficult problem because they turned out to want to come back, and we mailed them off to another site.
But even with the troublesome pigeons gone, the mysterious signal would not disappear.
And so we were left with the almost inescapable conclusion that this radiation was coming from the sky. I could not account for it.
The strange signal detected by Penzias and Wilson would turn out to be one of the most important scientific discoveries of all time. But the explanation for their mystery background noise starts not with sound, but with the birth of light. We usually take light for granted. But in the early universe, 13 billion years ago, we would see nothing at all. Light was trapped. The universe was foggy. Imagine a flashlight beam in a fog of smoke. The light bounces back and forth between the smoke particles and is trapped. In the hot baby universe, a dense fog of electrons blocked the light from escaping. But as the universe continued to expand and cool, the electrons slowed down. Protons then grabbed these calmer electrons to form complete atoms of first hydrogen and then helium. The universe was suddenly much less crowded with electrons. The fog lifted and light was no longer trapped. It hurtled out across the universe, creating a blinding burst of light.
Had we been there, we would have suddenly seen this opaque universe become transparent. Suddenly the fog would lift and we would see a flash of light coming from everywhere around us. It must have been a spectacular moment.
Over time, this burst of light dimmed and cooled and became microwave radiation. It was this faint 13-billion-year-old microwave signal that Penzias and Wilson picked up on their antenna. What they heard was the quiet echo of the moment the universe formed the first atoms.
It's really the light from the origin of the universe. If you have an old FM receiver, if you tune between channels, turn the knob, and it doesn't capture it and pop to a station, you get to a part where there's none, you hear a, that's what we call noise. If you have a good radio set, 0.5% of that is actually the sound of the Big Bang.
And we can also see the moment when the first elements were created. If our television is not tuned to a station, a tiny fraction of the noise is radiation from 13 billion years ago. But this radiation is not the only reminder of the birth of the universe. Even the water we drink is a memento.
And it's kind of amazing to think that every time we take a drink of a glass of water, we're drinking in atoms that have been around since the Big Bang, the hydrogen atoms.
Over the next millions of years, the young universe continued to expand, cool, and get dark again. So far, the universe had only made hydrogen and helium atoms. But the world we live in is made from more than 100 different kinds of elements. Without them, the universe would remain a very boring place, made up of only gas, a place where complex matter, like planets, cars, and people, could never develop. The universe needed to get hydrogen and helium atoms to fuse. And to do that, it needed to make stars. The universe was now 200 million years old and billions of light years across. Its temperature had dropped so far that it was colder than liquid nitrogen, minus 367 degrees Fahrenheit. It was also dark. It would have remained a very gloomy place, full of gas, but without galaxies, stars, or planets, if it hadn't been for one thing. The baby universe wasn't born perfect. Carlos Frank has created an amazing 3D simulation of how the early universe evolved. It shows that when the universe emerged from the Big Bang, it was uneven.
Little cracks appeared, which were very, very, very tiny, very, very small. And it was this rush in the face of the baby universe that later developed into the patterns that we see in the galaxies today.
Without these cracks, the universe would have been a very dull place. The first clues as to how these cracks developed into galaxies and stars came when other scientists started to examine the Big Bang radiation first discovered by Penzias and Wilson.
So what Penzias and Wilson saw was this radiation was, as far as they can tell, uniform. What cosmologists then did for the next 25 years was work very hard to try to find tiny variations.
And find them they did, using WMAP, a space probe designed to detect and analyze in detail variations in the background microwave radiation. Launched in 2001, the $150 million probe was fitted with some of the most sensitive instruments ever carried into space. Our eyes detect only visible starlight, but WMAP can tune into the invisible microwave radiation. Once in orbit around the Sun, it picked up the faint radiation that has been rippling around the universe since the dawn of time.
So when we look at the cosmic background radiation, we're looking at this radiation that's been streaming towards us since 500,000 years after the Big Bang.
Initially, the microwave universe looked very dull and seemed to be the same everywhere. But when WMAP turned up contrast, the results were spectacular. The baby universe wasn't smooth and boring at all. It was full of fluctuations.
These tiny fluctuations tell us what the variations in density, how much stuff there is, and how it varies from place to place. These denser regions are going to collapse to form clusters of galaxies and superclusters and galaxies themselves. These low-density regions, these will grow and become the empty regions between galaxies. So this picture really is our connection between the universe when it was a baby, 500,000 years old, to the universe today, 13.7 billion years old.
These tiny imperfections in the fledgling universe would become galaxies and stars.
And this is one of the most amazing propositions in physics. The idea that galaxies like a Milky Way that contain 100 million stars once began life as a tiny little crack in the fabric of the universe.
The material in these cracks was filled with swirling clouds of hydrogen atoms. The voids between the clouds grew bigger and bigger. The gas clouds got denser and hotter. Gravity pulled the gas clouds together on filaments, like beads on threads of a web, cosmic web. Where the giant filaments formed large globs, stars and galaxies would grow.
As the universe evolved, gases were able to condense into clouds, which collapse to form stars. The stars settle into a rotating disk that was later to become a spiral galaxy like the Milky Way.
Over millions of years, the hydrogen atoms clumped together and heated up. The atoms began fusing and releasing energy, and the gas clouds started to burn brightly. Eventually, a star was born. All over the universe, millions of stars ignited for the first time.
The appearance of the first stars would have been a truly spectacular event. Had we been there, we would have really seen fireworks. Individual, enormous flashes of light generated as the stars are born and burn themselves out.
The universe has expanded many trillions of times its original size. It was full of newborn stars made of hydrogen and helium. These young stars were nothing like our own sun. They were very unstable. But it was their instability that would make the universe a more interesting place, because deep inside each new star, something amazing was happening. They were creating new elements. The idea that stars build atoms came from the British astrophysicist Sir Fred Hoyle, one of the greatest astronomers of the 20th century. Hoyle didn't believe that the universe began in a single explosion. In fact, he coined the name Big Bang as a term of derision. Hoyle wanted to know where the elements heavier than hydrogen and helium came from. He figured out that stars acted like nuclear reactors, working a bit like a hydrogen bomb in slow motion. But many billion times more powerful, and their nuclear waste was new elements. But it would take years before scientists were able to confirm his theory by analyzing the light from stars. Each element emits a light at a particular frequency when heated up. Imagine a sodium street lamp. It emits light of a yellow color specific to sodium. It's the same with stars. Take our sun. If you break the light down into a spectrum, you can see lines like a barcode corresponding to the elements. Each element has specific colors, helping scientists identify elements like hydrogen, which emits mainly red light.
We are go for main engine.
In 1990, NASA launched the Hubble Space Telescope to unravel some of the mysteries of our early universe.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Hubble promised scientists unprecedented views of the young universe. It would be able to look back through space and time and examine early stars to discover if they were making new elements. But the dream soon turned into the worst nightmare. After it was launched, they discovered that Hubble's mirror was distorted. It saw everything out of focus. It needed corrective lenses. And the only way to fix it was to send up another space shuttle. One of the repairmen was astronaut Jeff Hoffman.
We were working with a $2 billion telescope, and the last thing we wanted was to break something and leave it worse off than when we got up there.
First, the crew of the rescue mission had to capture the crippled telescope. Then execute a repair mission unprecedented in the history of spaceflight. First, they had to open the access doors on the side of the telescope.
The one thing about working on Hubble that is very different from working on a car is you look over your shoulder and there you are in space. The Earth is going by below you, the stars above you.
The astronauts had to carry out fine, detailed work in the most difficult conditions.
When you're working in a spacesuit, your hands are encumbered by thick, stiff gloves. It's sort of like working in ski mittens, and it was quite a challenge.
All went well until Hoffman attempted to close the huge access doors.
I just had to close up the doors, and when I went to close them, they wouldn't close properly. The doors were somewhat warped, and it took a while for it to sink in. This was very serious. If you can't get the doors closed, you lose the telescope.
Using improvised tools, Jeff and a colleague were finally able to close the doors. It took the team 5 days to repair the stricken telescope. Cosmologists around the world held their collective breath. They waited to see if the most expensive telescope ever built would deliver what its designers originally promised.
I well remember New Year's Eve, 1993, December 31st, when my phone rang, and it was an old friend who worked at the Space Telescope Science Institute in Baltimore. He said, "Jeff, do you have any champagne left over from your party?" I said, "Yeah, we still have a half bottle in the refrigerator." He said, "Well, crack it open again and drink a glass because we got the first picture back and Hubble works."
This is what Hubble saw. The images were beyond anyone's wildest dreams. Hubble captured the final moments of a star's life when it explodes and blows off gas and dust. It also captured interstellar nurseries of newborn stars, exploding into life billions of years ago, and dark pillars of cosmic dust, millions and millions of miles long, ready to spawn a new generation of stars and planets.
I guess it's hard to surpass the famous pillars of creation in the Eagle Nebula, where you actually see the birth of stars. I mean, it's almost biblical. Let there be light. And I still kind of get goosebumps when I look at it.
But Hubble's true moment of glory was still to come. Over a 10-day period in 1995, the mission controllers pointed the telescope at a distant empty patch of space. What emerged was the deep field image, a tapestry of distant galaxies. Hubble was looking back in time to some of the first galaxies and stars created.
It revealed thousands of galaxies that hadn't been seen before, so the universe became, to our consciousness, far richer after the Hubble Deep Field.
It showed for the first time faint images of galaxies formed just 1 billion years after the Big Bang. Scientists then examined the spectrum of light from these distant stars and showed that these early galaxies had already created elements heavier than hydrogen and helium. Sir Fred Hoyle may have been wrong about the birth of the universe, but he was absolutely right about the stars. The early stars acted like giant thermonuclear reactors, creating new elements.
You can think of the creation of all the elements in this room as, in some sense, like a car assembly line. Because in a car assembly line, each part is sequentially added to the vehicle until it's complete.
Fusion reactions inside these young stars released enormous amounts of energy and heat, which forced atoms to fuse to form new, heavier elements, one after the other. 3 helium nuclei combined to form carbon. 2 carbon nuclei fused to form magnesium. Magnesium to form neon, and so on over a period of hundreds of thousands of years, until silicon fused to form iron. Iron is a very special atom. The protons and neutrons inside its nucleus are very tightly bound together, so that even the extreme temperatures inside the stars couldn't get it to fuse into heavier elements. It resolutely stays iron. It was the end of the road. The production line of element building shut down. But our universe was still not complete. There were all the ingredients to make a glass of water, and some of the elements to build much of our convertible. There were also quite a few of the ingredients to make a human being: the oxygen we breathe, the calcium in our bones, and the iron in our blood. But there still weren't any of the vital ingredients like chromium for our car fender, and some metals like zinc that our bodies can't survive without. The universe was about to enter a super creative phase where it produces all the elements heavier than iron. To make the missing pieces in our birth of the universe jigsaw would take some of the most powerful explosions the universe has ever seen. Our universe has already celebrated its 500 millionth birthday. There are still another 13 billion more to go before humans appear on the face of the Earth. Giant new stars have made many of the elements in the world we see around us. But some vital elements are still missing. Heavy metals like chromium and zinc, and expensive ones like gold and platinum. To finish the job, the universe conjures up the most amazing phenomena since the Big Bang. Massive exploding stars called supernovas. When the giant stars that made the lighter elements ran out of fuel, they collapsed in on themselves, creating incredible amounts of energy and enormous explosions. These explosions were so powerful, they could fuse elements even heavier than iron and restart the element production line. Tony Metzacappa from Oak Ridge National Laboratory in Tennessee believes that without exploding stars, life itself would not exist.
Life as we know it certainly would not exist were it not for core collapse supernova events. They are very clearly one of the key links in our chain of origin from the Big Bang to the present day.
One of the most recent and biggest supernovas closest to our galaxy was seen in the southern hemisphere in 1987. When a supernova like 1987A explodes, it emits light containing the signatures of the elements within it. By examining this spectrum of light, scientists can calculate what elements are being forged inside the exploding star. Michael Smith from the Experimental Astrophysics Group at Oak Ridge then recreates these events inside his own star laboratory. In this 100-foot tower, he accelerates and smashes individual particles into each other, just like inside a supernova.
These subatomic nuclei are the ones that are absolutely crucial in the formation of the heaviest elements. So the idea is to measure exactly how fast these nuclei will fuse together in the laboratory, and then translate that information into how fast they'll fuse inside exploding stars.
When the particles collide inside the accelerator, they generate enormous energy. In these extreme conditions, the particles fuse.
And then you can bring other particles in, and they will fuse. And we believe that exploding stars are just right to form elements much heavier than iron, going all the way up to the top of the periodic table.
Using the data from these experiments, Tony Metzacappa has created a model of how these massive exploding stars turn into heavy element factories.
Massive stars, they evolve to an onion-like configuration at the end of their lives. They have an iron core, and outside of the iron core are layers of successively lighter elements.
Inside the iron core, the temperature rises to 8 billion degrees, nearly 300 times hotter than the center of the sun. It is so hot that the iron atoms that have sunk to the star's core are torn apart. The core destabilizes.
The cores then collapse on themselves in a fraction of a second. The collapse proceeds to very, very high densities.
The core collapses at speeds of more than 43,000 miles per second. A volume the size of the Earth crunches down nearly 6 times the size of Manhattan in an instant. The core becomes super dense.
If one were to take 1 cubic centimeter of that matter, that would be the size of a sugar cube. That sugar cube would be so dense that it would weigh as much as the entire human race.
The core rebounds like a compressed rubber ball and launches a massive shockwave. The shockwave hurtles out, smashing through the different skins of the star. As it punches through the outer layers of the star, the energy generated restarts the element production line. Atoms are smashed together to make brand new, heavier elements, all heavier than iron. Then the star explodes, and the shockwave pushes the shrapnel-like debris outward, further and further into space.
In a very real sense, our lives depend on the stars in the universe. Without their lives and deaths, we would not be here today.
These astonishing images taken by the Hubble Space Telescope show the aftermath of these giant explosions. Nebulae, giant clouds of debris thrown off by exploding stars. Swirling inside are big new atoms, gold, silver, zinc, and lead. Without supernovas, our world would be a very dull place and possibly lifeless.
So I'm sure that Paris Hilton doesn't wake up every day thinking about this fact, but really, if it weren't for exploding stars, those 200 million stars that exploded so we could be here today, she wouldn't have anything to wear. So if it weren't for those supernova explosions, there wouldn't be any bling.
9 billion years after the Big Bang, and all the ingredients are in place for life as we know it. The universe has grown up into a vast, complex place made up of billions of galaxies and uncountable stars. In a quiet corner of the Milky Way, a mass of dust and gas begins to accumulate. It's full of the rich debris left over from one of the massive supernovas. And when it reaches a critical mass, it begins to burn brightly. A star is born, our own star, the Sun. What's left over forms a disk of swirling debris in orbit around the new star. The gas and dust that make up this ring collide, pulled together by gravity. The clumps of dust and gas become bigger and bigger. Planets form. One of these planets is our Earth. Over the next 500 million years, our planet slowly generates a protective canopy of gas, the atmosphere. The first life appears, just single cells at first. But as the eons pass, those tiny single cells evolve into plants and animals, and eventually humans.
We tend to disassociate ourselves from the universe, but that, of course, is completely wrong. We are a vital part of the cosmos. And so when we talk about the origin and evolution of the universe, we're actually talking about the origin and evolution of ourselves.
Everything we can see on our planet was either made in the Big Bang or inside a star. Scientists like Krauss believe they now know the genesis of every atom that has created the world we live in.
These atoms have been around since the dawn of time. And when I was young, my mother used to tell me, "Don't touch that, you don't know where it's been." And she would have been amazed.
But this is not the final chapter in the story. After almost 14 billion years, the universe has really only just gotten started. Now we take a journey into the future to see how it all ends. The universe we live in is nearly 14 billion years old. It has created the raw materials for everything we see around us: the stars, the planets, trees, cities, automobiles, even us. Our world is complete, but the universe is still evolving. Scientists have come up with many theories on how it will end.
We know our universe began in a Big Bang. What we don't know yet is what the future of our universe is going to be. Our universe may end with a bang or a whimper or something even more exotic.
One theory suggests that our universe will run out of steam and stop expanding. Every star, galaxy, and planet, every atom will start to collapse, ending in a single super dense pinpoint known as the Big Crunch. To find out if the universe really is going to crash back in on itself, scientists first need to discover if it's still expanding or if it's slowing down. Astrophysicist Saul Perlmutter studies the death of the universe by finding beacons in space, exploding stars called Type 1a supernovas.
If you have enough of these exploding stars, these supernova, that you've measured their brightness, so the ones that look fainter and fainter and fainter must be further and further and further away. And so you have some supernovae that are a little bit brighter, they're more nearby, some that are a little bit fainter, so they're a little bit further, and some that are very faint, so they're very far away.
Type 1a supernovas are similar to the supernovas that created the heavy elements. They differ in one important fashion. They always explode with the same exact brightness. This is because they are created in the same way. Two stars circle each other, held together by their gravitational attraction. One is shriveled and super dense, glowing with white heat, a white dwarf. The other star has bloated to an enormous size. It's a red giant that is burning the last of its fuel. As the two stars orbit each other, the white dwarf sucks gas from its companion and begins to grow year after year. When it is precisely 1.44 times the mass of our Sun, the white dwarf crumples, collapses, then explodes, releasing a blinding burst of energy. Every Type 1a supernova explodes at the same tipping point, and so are equally bright and visible across the vast distances of the universe. Perlmutter needs to find hundreds of Type 1a supernovas and then measure how fast they are moving away from us. He links up the most powerful telescope on Earth with the most powerful in space. Using advanced cameras on the Hubble Space Telescope and a giant telescope officially known as the Very Large Telescope, or VLT for short, he hunts for supernovas. Once Hubble has detected a particular light source, colleague Chris Lidman at the VLT analyzes the object to see what it's made of and make sure it's a Type 1a supernova.
This object is a distant galaxy, and next to it is what we believe is a distant supernova. The next crucial step is to understand what type of supernova this is.
The VLT breaks down the light from the object into its spectrum.
You want to be able to break up its light into a spectrum and look for the very characteristic fingerprint that you would see if it really were a Type 1a supernova.
The light emitted from this particular supernova reveals that it's a Type 1a. Lidman can now calculate how far away this supernova is.
The supernova exploded about 7 billion years ago.
By comparing the positions and dates of all these supernovas stretched over space and time, Perlmutter can calculate whether the universe is slowing down. His results are a shock. The expansion of the universe isn't slowing down at all.
When we began the project, of course, the goal was to find out how much the universe was slowing down. Now, when we actually started looking at the data, it looked like the universe wasn't slowing enough to come to a halt. And in fact, it wasn't slowing very much at all. And in fact, when we finished the analysis, it looked like it wasn't slowing, period. It was actually speeding up in its expansion.
Perlmutter's astounding discovery means that the universe will not grind to a halt, then crunch back down into a pinhead of superdense matter. Quite the opposite. It will continue to expand faster and faster. Our universe is literally flying apart.
The expansion of the universe will accelerate at ever faster and faster rates until literally everything will get ripped apart. Not just galaxies, but eventually matter, the Earth, all the objects, stars, the Earth, planets, people, atoms, in a finite time would get ripped apart.
Long after our sun has burned out, 100 billion years in the future, galaxies will pull apart. The universe will be made up of isolated stars, which are running out of energy. Some will become white or brown dwarfs. Others will collapse into neutron stars or black holes. Then, thousands of trillions of years after the Big Bang, even the black holes will evaporate, and all matter will decay to its basic ingredients. Atoms will fall apart, and even protons, the building blocks of atoms, will decay.
The most likely future is perhaps the most dismal one, where the universe becomes cold and dark and empty.
As the universe continues to expand and the galaxies speed apart from each other, space will become empty and dead.
Our own cluster of galaxies will be moving away from us faster than the speed of light and will disappear from the night skies.
Eventually, everything will just sort of wind down, and that's the end of things.
Sunrise, a daily celestial wonder, bringing the heat and light that keeps us alive. We bask in its rays, and yet most of the time, we take the sun for granted. We think it's always been there and expect it always will be. Our only worry is sunburn. But the truth is very different. The sun can wipe out our most advanced technology, be as powerful as nuclear explosions, and can put our lives at risk. And in the future, as the sun ages, its glorious energy will become a nightmare, driving humans off the face of the planet, potentially threatening our very survival as a species. Understanding what will happen to the sun is something that astronomer Don Brownlee knows about.
The sun lasts a very long time, but it doesn't last forever. All stars have a limited lifetime, just like all people have a limited lifetime.
Our lives on this planet are inextricably linked with the sun's life cycle. But how do we know about the sun's life, when it was born, and when it will die, especially when scientists are dealing with time spans of billions of years?
No forester ever watches a redwood tree grow for 3,000 or 4,000 years, and yet we absolutely know the trees start as little seedlings, they get bigger, they get giant, and eventually they die. Likewise, see millions of stars in the sky, and you're actually looking at stars in all the stages of evolution.
The sun is a star, just like those that fill the nighttime sky. So looking at other stars reveals fascinating details about our own sun's life. This is a stellar nursery around Orion's belt. Young stars less than 1 million years old are forming here right now, just as our sun did billions of years ago. This sundial represents the life of our sun, traveling from the distant past, starting with the sun's birth at dawn, 6 a.m., through till its death at dusk, 6 p.m. Right now, it is exactly 6 in the morning. The sun is being born. The sun is forming within what scientists call a molecular cloud, the dust and gas debris from hundreds of exploding stars. The molecular cloud is mainly made up of hydrogen, the most common element in the universe. Gravity draws the atoms together, so that over the course of 1 million years, the cloud collapses in on itself. Gradually, more and more material clumps together at the center. It's a bit like when fire dancers make circles. The further away the fire is from their hands, the slower it rotates. If the dancer nearest the camera makes a tighter circle by bringing the fire to the center nearer her hands, it rotates faster and faster. And it's the same in the molecular cloud. Molecules rotate more quickly in the middle, which becomes denser and denser, until the atoms in the center become so packed, so compressed, they heat up.
As I put compressed air into this model sun, I can feel it heat up, like hydrogen compressing when the sun was forming. And this is how the sun got hot and began the fires that warmed the Earth for billions and billions of years.
The temperature of the cloud soars to millions of degrees, so hot that the hydrogen atoms slam into each other and fuse. Huge explosions of energy are released. The force of these explosions pushes outwards against the force of gravity. Throughout its life, the sun will be in an endless tug of war between these two forces. But now, there's a stalemate. The pressures balance each other. The sun is born. The sun crushes together more than 99% of the original molecular cloud. The little bit that's left then forms the Earth and the other planets in a disk around the sun. Scientists generally agree on this model of how the sun was born. But theory is just theory. The sun is 93 million miles away, which makes real physical evidence hard to come by, at least until now.
3, 2, 1.
August 2001. NASA launches its most ambitious mission to the Sun so far, Genesis. At Houston's Johnson Space Center, bringing a piece of the Sun back to Earth has been a 10-year dream for Eileen Stansbury.
The chemical composition of the Sun is like a fingerprint of the original solar nebula, and being able to catch a piece of Sun and bring it to Earth to analyze is exciting.
Stage level's still looking good, and we just went supersonic.
But how do you catch a piece of the Sun? Even the outside halo, known as the corona, is up to 3 million degrees Fahrenheit, a temperature no space probe could survive. The answer is to steal a bit of the solar wind, a stream of particles blowing away from the Sun at speeds up to 500 miles per second. But the Earth is shielded from the wind by an invisible magnetic force field, the magnetosphere. So until now, we haven't been able to get our hands on it. To get around that problem, the Genesis spacecraft travels deep into space, 1 million miles from Earth. Here, wafer-thin strips of gold, sapphire, silicon, and aluminum, among the purest and most durable materials on Earth, are left to sunbathe in the solar wind. It's a little like dropping marbles into a children's ball pool. Scientists hope as particles in the wind hit the wafers, they will force their way deep inside the layers of molecules within the gold and other materials.
And those marbles will embed themselves within the gaps in the balls. And that's how the solar wind embeds itself within these pure materials.
Meanwhile, down on Earth, the success of a daredevil plan to catch the returning capsule in midair rests on a Hollywood stunt pilot. Fresh off the movie Mission Impossible 3, Cliff Fleming has his own impossible mission to complete. Fleming's task is to hover at an altitude of 10,000 feet, waiting for the capsule to parachute out of the sky.
This pole here was attached to the helicopter. It's about 20 feet long.
Then, Fleming will swoop down 8 feet over the parafoil and grab the 420-pound payload in mid-flight before lowering it safely to the ground. In 5 years of training, Cliff Fleming has a 100% success rate, catching a dummy capsule 11 times in 11 attempts. But these were just rehearsals.
In Hollywood, our film we work on, there's take after take. In this case, there's only one chance.
And having spent over $200 million on the Genesis mission, that one chance to catch the real capsule will be crucial. September 8th, 2004. 3 years after its launch, having collected atoms from the Sun for 884 days, the Genesis capsule begins its journey home. It's the culmination of years of planning and training to ensure that its valuable cargo arrives safely and provides scientists with the purest pieces of the Sun ever to be studied on Earth.
We were anxious.
You had the adrenaline flowing that morning.
I've been working on this mission for a decade.
The capsule re-enters the Earth's atmosphere and, as planned, heads toward the Utah desert where Cliff Fleming is waiting to catch it.
I felt like I was just a center fielder out in a baseball field waiting for the pop fly to come in, and everything was right on time.
Right on time, back in the control room, the capsule comes into view. But something's not right.
It's not supposed to tumble. We knew that something was wrong.
The parafoil is supposed to slow the capsule down, but it hasn't opened. The capsule tumbles out of control, and there's no way that Cliff Fleming can possibly catch it. The capsule hits the ground at over 193 miles an hour. It splits open, and the priceless wafers shatter into thousands of pieces. For the members of the Genesis team, it's potentially a disaster.
Shock, and there was silence.
my whole crew was quiet, and we're disappointed.
And back at NASA, they have a mammoth task ahead to salvage useful results from the mission. Recovering the precious solar samples from the broken gold and sapphire wafers is crucial. The major problem they face is removing the contaminating dirt from the impact, but they hope that the actual samples are still safely embedded deep within the wafers. They also have to ensure that they don't contaminate the samples further. By measuring how much dirt and top layers to remove, the scientists hope to rescue the pure solar samples beneath. These samples are made up of atoms and ions, which are atoms stripped of many of their electrons. They're minute, and the whole sample weighs no more than a few grains of salt.
They're so tiny you can't even see them, but we collected billions of these atoms and ions to analyze.
Most of the sun is made up of hydrogen, but scientists also expect to find silicon, oxygen, carbon, nitrogen, magnesium, and iron among the billions of atoms they've collected. All the elements are made up of a blend of atoms called isotopes. Scientists already know that some elements blended differently in our solar system. Only the sun contains the original blend from the molecular cloud from which every other blend came.
It's an exciting opportunity to view back in time to the very beginning, to the birth of our solar system, and try to understand where we came from.
The team has already successfully extracted the first atoms, but it will take time before they can answer all these questions. What they already know is that planet Earth is uniquely located to benefit from the sun's light and heat, and that is vital for life. We're in the temperate or Goldilocks zone of the solar system. Not too hot like Mercury and Venus, and not too cold like Mars. Instead, it's just right for life to flourish. It's 10 a.m. on our sundial, 4 billion years after the sun was born. Animals are just appearing. 35 minutes later, humans walk on Earth, our bodies created out of carbon, originally from inside a star. And today, we rely on the sun for our very survival. Its energy fuels trees and plants, which are essential for the food chain we all depend upon. And by evaporating water from the oceans to form clouds, the sun supplies us with rain to nourish our crops and fresh water to drink. This energy is created more than 93 million miles away at the heart of the sun's nuclear engine. At temperatures in excess of 27 million degrees Fahrenheit, 4 hydrogen nuclei fuse together to create a single helium nucleus. But the helium is slightly lighter than the 4 hydrogen nuclei, and it's that missing material which is converted under Einstein's famous formula, E equals mc squared, to pure glowing energy. It's given off as tiny particles of light called photons. Every sunbeam is full of them. Every second, almost 600 million tons of hydrogen are converted into helium. That's more energy in 1 second than 6 billion nuclear power plants would produce in a year. But how does the energy reach us? The incredible journey that photons make to deliver energy to Earth is something David Bodanis, a solar expert, knows all about.
Those photons of light that come down and give you a tan after a while were created over 1 million years ago, and some were starting their journey when the dinosaurs were still around.
They battle their way through the biggest obstacle course in the solar system, starting in the sun's dense core. Here, photons zoom around at the speed of light, bumping into electrons. As they collide, photons pass on energy or momentum, just as one ball does to another on this executive toy.
They pack this terrific punch. It's just like a sequence of balls suspended on wires. If you take one back and whack it into them, the momentum pushes all the way through and makes the one on the far side fly out.
The next obstacle for the survivors is the radiative zone. Here, photons are bounced around by particles of hot hydrogen gas called plasma. They start changing direction in random ways, a bit like balls in a pinball machine, zigzagging around for years and years and years.
The photons in the sun have a journey as hard as these pinballs that spends 1 million years in the radiative zone, and they're hitting against each other all the time, backing sideways, going backwards, occasionally going forward. For some of them, it's been the entire length of time since the sun was formed, and they still haven't made it out.
Only the lucky ones make it out to reach the convection layer, where they get a bit of a rest. In just 3 months, they're absorbed in seething rivers of hot gas and carried by their currents to the sun's surface, the photosphere. Here, the hot atoms enter the sprint section of the course. They cool and release their energy as photons once more. The photons stream into space, and traveling at the speed of light, they complete the 93 million mile journey to Earth in just 8 minutes. Finally, they arrive. Photons have been providing heat and light since the sun started glowing. By 10 a.m., the conditions they helped create gave us animal life on Earth. But where are we today on the sundial? Exactly how old is the sun? Scientists know its age because of one remarkable fact. The sun sings. It doesn't really play a tune, but scientists have discovered that massive pressure changes deep within the sun cause vibrations that resonate through to the surface and bounce around inside the sun like sound waves or seismic waves on Earth. This is the sound of the sun singing. To allow us to hear the sun's voice, scientists speed up the frequency of the sun's oscillating pressure waves 42,000 times and compress 40 days of vibrations into just a few seconds. Work on calculating the sun's age from its singing was carried out at Big Bear Observatory in California by astrophysicist Phil Goody. We know that the sun's temperature and pressure change more and more over time. Phil Goody and his team have worked out that these changes would cause the sun to sing a different song.
This is much like the case of a drum. I put my fingers on and increase the pressure, I get a higher frequency, a higher pitch. And when I take my fingers off, I hear a lower pitch. It's as though the drum, when it ages, it gets softer.
Just like the drum, as the sun ages, changes in its density, pressure, and temperature cause the sun to sing at different pitches. But unlike the drum, which loses pressure as it gets older, the sun's pressure increases, making the pitch higher. Scientists calculated at what pitch they would expect the sun to sing at each stage of its life. Finally, they matched today's song to those calculations to find out its current age.
We've been able to precisely determine the age of the sun to be 4.6 billion years old. So that's kind of a surprise.
Their discovery makes the sun millions of years older than they had previously thought. On our sundial, in which 6 a.m. marks the birth of the sun and 6 p.m. its death, we are now at 10:36 a.m. Humans have only been around for less than a second, and we're reaping all the benefits of its warmth. But it won't always be like that. The sun's heat will slowly increase until it becomes too dangerous for human life. And even today, during the sun's golden age, it already brings many dangers that we are only beginning to understand. Using the latest optical imaging techniques to see what's happening on the surface of the sun, Scientists are learning about sunspots, solar flares, and the hurricanes they release into space.
The sun's not alive, but sometimes it has the feeling as though it is because it looks angry.
March 10th, 1989. The sun ejects a giant cloud of charged particles. 3 days later, the solar storm hits the Earth. In Quebec, Canada, 6 million people are about to discover just how angry the sun can be. The sun's warmth and light sustains life on Earth. But it can also play havoc with our modern way of living. Our world depends more and more on technology. Our cities rely on complex networks of power lines, and our communications depend on sophisticated satellites. They can all be wiped out by the sun. Billions of tons of high-energy particles erupting from the sun send powerful storms hurtling through our solar system. Our growing realization of how devastating these storms can be makes the job of space weather forecasters like Larry Coombs ever more significant. At NOAA's Space Environment Center in Boulder, Colorado, they try to predict the sun's violent moods. 1989 brings one of the most dramatic space storms that Larry Coombs has ever seen.
The storms were an eye-opening event for understanding what can happen when the sun has its violent moments.
March 10th, and a telescope in New Mexico captures this solar flare exploding. It sends an electrically charged hurricane toward Earth at a speed of more than 1 million miles an hour. 3 days later, it causes a huge electromagnetic storm over the northern hemisphere. At 2:44 in the morning, Quebec in Canada feels the full force. More than 1 million amps of electrical current overwhelm the power grid. Within seconds, power stations across the province go down like dominoes. 6 million people in Quebec are left without electricity. The blackout lasts for 9 hours. The only light in the sky that night is an unusual pink glow caused by the storm. The events in Quebec cause hundreds of millions of dollars in damages and loss of revenue. Now, the team at Boulder are on Sunwatch. Using live, up-to-the-minute satellite images, operating 24/7, they keep an eye out for any sudden changes in the sun's behavior that can cause disruptions, like in Quebec.
We look at sunspots, and these are these dark, gnarly-looking areas, and this is probably about the size of 14 Earths. We also look at prominences, which is this thing that's sticking out on the side of the sun. Both of these areas can create solar storms.
But how? Scientists believe that the sun's moods are determined by its complex magnetic fields. New magnetic fields are constantly being created because rivers of hot hydrogen gas, called plasma, which are electrically charged, flow at different speeds around the sun. The sun's rotation tangles these magnetic lines together, forcing parts of them to emerge on the surface as dark sunspots, and prominences that start sticking out from the surface. The plasma flows and field lines continue to build up as under this sunspot. Eventually, the field lines get so twisted, they snap like rubber bands and cause explosions. So once prominences and sunspots are seen, forecasters are on alert for explosions on the surface of the sun. Sunspots can be followed by solar flares. These are so powerful that they are like millions of megaton nuclear bombs all exploding at once, sending electrically charged radioactive particles out into space. Prominences just get bigger and bigger. Some end up looking like flares before they too blow up. Both flares and prominences can also be followed by even bigger eruptions in the form of what scientists call coronal mass ejections, or CMEs. When these occur, the sun discharges billions of tons of electrically charged gas. All these phenomena unleash high-energy particles, which carry electromagnetic fields with them to Earth, and they can disrupt equipment that is electrically conductive, such as a power line. At the California Institute of Technology in Los Angeles, they are trying to understand the science behind the sun's explosions. Solar physicist Paul Bellin makes his own prominences. He feeds the same ingredients that make up the sun into a vacuum chamber,
1 kilovolts,
sets up a magnetic field, adds hydrogen plasma, and then drives very large electrical currents along the field.
3 and fire. Our laboratory prominences are a nice human size, about this size. Prominences on the sun are typically 60,000 miles, and the sun is just full of them.
Real prominences can grow for days or weeks before they suddenly explode. In the lab, the whole process takes microseconds. But by using a high-speed camera and colorizing the images to see more detail, Bellin's team can watch the effects in slow motion. As the magnetic forces increase, the fields begin to arch and twist up.
And they're really the same as the kinds of forces that you have between magnets. Here, 2 magnets attracting each other, or 2 magnets repelling each other. See, I can't bring them together. So on the sun, some of these forces are attractive, and they will cause prominences to merge with each other, for example. And the force that makes the prominence blow up is a repulsive force.
Normally, solar wind carries about 1 million tons of electrically charged gas particles away from the sun every second. But when these explosions occur, the storm clouds of additional particles are more dangerous. The Earth's magnetic field, or magnetosphere, which protects us from solar wind, is overwhelmed. Usually, it deflects the particles toward its weakest point, the poles. Here, they react with oxygen and nitrogen in the atmosphere to create streams of different colors, a phenomenon known as the aurora, or northern and southern lights. But when strange lights appear in the sky away from the poles, as in Quebec, they are a sign of intense solar storms breaching the magnetosphere. Boulder, Colorado, September 6, 2005. Larry Coombs and his colleagues monitor an intense solar storm.
As we're speaking right now, we're having a strong solar flare going on. If we look at the blue image, we can definitely see the energy being blown out from the sun at millions of miles per hour.
The sun experiences one of its violent moods, producing explosion after explosion after explosion. Northern lights appear all over America. This time, it's not the power grid that's affected, but communications.
High-frequency communications, radio blackouts are occurring with our aircraft. We're also having problems with satellite phones as well. If we look at our plots up here today, we can see that this activity is affecting the Atlantic and the Pacific. So both ways, communications are blacked out.
We've got 12 in progress.
Everyone wants an update, and the alert status is high, particularly for any airlines that fly near the poles, where the only communication is via high-frequency radio. During solar storms, high-frequency communications can be wiped out, blinding the pilot and risking the lives of passengers.
Great, thank you.
But if airlines get warned, they'll reroute or even ground planes. And it's not just the airlines that fear radio blackouts. Other communication systems can be knocked out. In space, satellites have been damaged, causing loss of signals. Imagine no TV. Imagine all cell phones stop working. But it's not just electrical damage and radio blackouts that these storms can cause. They can also increase the risk of radiation. Solar storm radiation is potentially dangerous for passengers on airplanes, but this radiation poses even greater dangers for astronauts out in space. Late October 2003. 3 huge sunspots appear on the sun's surface, one the size of planet Jupiter. A giant solar flare erupts from the surface of the sun, pointing straight toward Earth. And high above the ground, astronauts on board the International Space Station find themselves directly in the path of the deadly radiation the sun unleashes. Scientists know that the sun was born over 4.5 billion years ago. That's dawn on our sundial. It's now 10:36, and scientists have only learned about solar radiation in less than the last second. We all experience one form of solar radiation. It's sunshine, made up of ultraviolet light. Too much sunshine can cause sunburn and skin cancer. But the ozone layer protects us by blocking out the most harmful effects of UV radiation, and sunblock can do the rest. But there's one place where the type of solar radiation is much harder to protect against: space. Space travel has always been dangerous. But when astronauts first ventured beyond the Earth's atmosphere,
Godspeed, John Glenn.
they were completely unaware of solar storms and the radiation they caused. On August 7th, 1972, Big Bear Observatory in California monitored this flare, unaware of the level of danger. We now know it caused one of the largest solar radiation storms ever recorded. It's a legendary event at NASA because luckily it happened in the gap between Apollo 16's flight to the moon in April and Apollo 17's 8 months later.
You are go for orbit, go for orbit.
Had it occurred during either of these flights, radiation might have killed the astronauts. Scientists know that intense solar storms can be as dangerous to astronauts as the gamma radiation from nuclear blasts. Solar flares release a cascade of high-energy particles known as protons. Protons can pass through the human body, potentially causing chromosome damage and even cancer. Large doses of radiation can be fatal. And today, 30 years after the Apollo missions, NASA relies on space weather forecasts to protect astronauts against these dangers. While training to go into space, like most of us, astronaut Mike Foale had no idea how volatile the sun could be.
I thought I knew about the solar system and the environment, but when they talked about space weather, I went, space weather? What could that be?
Late October 2003. On board the International Space Station, Foale's about to find out exactly how dangerous space weather can be. The sun erupts in a series of events so powerful that they become known as the Halloween storms. October 28th, Boulder, Colorado. At the Space Environment Center, they watched the second largest flare on record explode from the center of the sun.
The problem was the location of it. It was what we would call in the kill zone, where all the energy's coming straight out toward the Earth.
In the line of fire is the International Space Station and Mike Foale. Larry Coombs has to warn NASA.
We were constantly in contact with NASA, as well as they were back and forth with us.
And NASA immediately warned Foale of the danger. They tell him to go to the most protected part of the station, the crew compartment, which is lined with polyethylene shielding. It offers some protection from radiation, although no area is completely safe.
Now you're in survival mode. You just deal with reducing the immediate deathly effects at that moment.
In 2 days, Mike Foale experiences as much radiation as he would normally receive in a week. The equivalent of being bombarded by dozens of X-rays on Earth. But it could have been a lot worse. If he had gone outside during the storm, he would have suffered acute radiation sickness, causing nausea and cellular damage within 10 minutes. There's one solar phenomenon for which there is no protection. And no one knows the cause. A superflare. Superflares are up to 10 million times more energetic than the most powerful solar flares. They can last for up to 1 week and cause stars to shine 1,000 times more brightly than normal. Breck Observatory in Baton Rouge, Louisiana. Looking for flashes of light in the sky is astrophysicist Brad Schaefer. He's found evidence of 9 stars that have produced superflares. At least 2 are almost the same size as our sun. And tonight, he's looking at Omicron Aquila, a star that's just 7% larger than our own sun.
For a 4-day period, this star was 10% brighter than normal. The total power in this flare was 1 million times more power than even the largest flare ever seen on our own sun.
What if our sun ever produces a superflare? What would happen to life on Earth? Schaefer believes everything in space would be fried. On Earth, every power grid would go down. Although the extra heat from a superflare would not in itself be dangerous, doing little more than turning a winter's day into a summer's day. And we'd see auroras all over the world. It might look pretty, but Schaefer fears that the level of radiation from a superflare would be lethal. It would destroy our ozone layer, the very thing that protects us from the sun's ultraviolet radiation.
The dominant killing mechanism is going to come from the radiation from the sun. Now, humans can go around and put on SPF 2000 sunblock and we probably live. We don't go out in the daytime. But our corn crops can't do that. You can't do that for the plankton in the sea, the whales feed upon, the food chain, top, bottom, and middle. They're all going to die.
It sounds scary, but Schaefer is optimistic that we're not at risk. On average, superflare stars have a superflare every century, and there's no evidence that our sun has ever experienced such a flare. But no one knows for sure what causes superflares, though Schaefer does have a theory. He believes that superflares occur if the star has a giant Jupiter-sized planet close by. They each have a number of magnetic fields, which become intertwined as they spin, forming bigger fields between them.
You can imagine my fist is a star, and there will be a planet going around that star. If you have a magnetic field which is attached to the star, I'm going to represent the magnetic field by this rubber band. Well, the magnetic field also can be attached to the planet. As the planet goes around, the rubber band and the magnetic fields are going to stretch and keep stretching, and ultimately they're going to snap, which was a release of energy stored in the rubber band.
If Schaefer's right, we'll avoid the effects of a superflare, but we won't be able to avoid the devastation the sun will cause as it ages. We're currently at 1036 on the sundial. By 1130, it'll be too hot for humans to handle. Our sun is getting hotter. Since its birth 4.5 billion years ago, its brightness has risen by 30%. And scientists predict that it'll get even hotter, evaporating our oceans, melting the surface of the Earth, and ending life as we know it. But how? We know when the sun was born, how it nurtured us, and how it has also thrown a fair amount of danger our way. But that's nothing compared to what happens to life on Earth as the sun heats up and dies, unleashing an inferno that will threaten the survival of humanity on Earth. Death Valley in California, one of the hottest places on the planet. It provides a hint of what the sun holds in store for all of us. Astronomer Don Brownlee shares his vision of that fiery future.
It's an extremely hot day here in Death Valley, but in fact, in the future, the entire planet will become much hotter than this. As the sun ages, it gets brighter and brighter and brighter, about 10% every billion years.
Step into the sun's distant future. The hydrogen fuel is slowly running out, but the nuclear reactions at the heart of the sun are not slowing down, they're speeding up. Pressure at the core drops as the fuel is burned. Lower pressure no longer holds the forces of gravity at bay. Now gravity compresses the core, which heats the hydrogen up even more and makes the fuel burn faster. This increases the pressure coming from the core. The two forces balance again. But it's a cycle that continues as more fuel is burned and the sun gets hotter and hotter.
Eventually, the sun will get so hot, it'll actually melt the surface of our planet, believe it or not.
On our sundial, shadowing the course of the sun's life from its birth at 6 in the morning to its death at 6 p.m., we are now at 10:36 a.m. At the moment, Earth is ideally placed in the solar system. It's not too hot or cold. As the sun heats up, the danger zone will move outwards, scorching the Earth. This will start a catastrophic chain of events that reads like the ultimate disaster movie. We'll lose our jungles, forests, and farmland as the desert grows, turning the surface of the planet into a giant series of sand dunes. Animals will be the first to be hit by the growing heat. They can't protect themselves as easily as humans can. Now things go from bad to worse, much worse. The increased temperature speeds up the removal from the atmosphere of the carbon dioxide that plants need to survive.
Plants virtually disappear from this planet, and anything that eats plants for a living also goes with it.
The glowing heat that gave us life now becomes so strong that it kills off the rich diversity of life on Earth. And as plants disappear, the oxygen they produce declines, making it harder for humans to breathe. We'll also lose most of our food supply. But even at this stage, some humans will probably still be around.
People are very adaptable and very wiry. I think it's very likely that humans could be the last animals on this planet.
Scientists don't agree on the exact date humans will disappear from the face of the Earth. But in 1 billion years from now, at 11:30 a.m. on our sundial, they predict on average it could be as hot as 160 degrees Fahrenheit. By then, the daytime heat could kill us. If we're still around, we may live underground and only come out at night.
People have two options. We can build more and more sophisticated artificial environments on our own planet, or we can potentially go elsewhere. I know it's a common belief that we are destined to live somewhere in the outer solar system.
If we're going to survive as a species, we are going to have to find a new home, especially once the Earth's water starts to vanish. As the sun keeps getting hotter, Earth also gets hotter, and more water evaporates until all our oceans disappear. And it's this disaster that will make human life on Earth impossible. In Death Valley, the lake at Badwater dried out 10,000 years ago, leaving just salt flats. It's an eerie foreshadowing of what's to come.
I would describe this area as totally alien. It looks like we're on a different planet, but it's our planet, and all of our planet will look like this.
And from space, it will look alien too. Gone will be the blue and white planet covered with water and vegetation, to be replaced by a planet that looks more like Mars. By now, we need to be long gone from the neighborhood, moved to another planet, mere spectators to what the sun does next. Now the sun swells and changes color from yellow to red. It is becoming what astronomers call a red giant, an old star entering the last stage of its life. It completely fills the daytime sky. The atmosphere has gone, and it's like looking into space. It is some 6.5 billion years from now. On our sundial, we are nearing dusk. And though the sun's now a senior citizen, it's more active than ever. Now the sun uses up the last of its hydrogen fuel in the core. It's burning helium, which burns ever hotter. The energy radiating out from the superheated core pushes the upper layers of the sun outwards, making it bigger and bigger. As it grows, the surface gradually cools, making it appear redder in color. Although the outer layers of the sun are cooling, the sun is reaching out toward us across the solar system. And just like stepping closer and closer to a fire, the Earth feels more and more heat.
When the sun becomes a red giant, it's a dangerous phase for a planet like the Earth. It's quite spectacular. It becomes very much brighter, very much larger. Its heat will fry the Earth.
By now, the surface of the Earth has long melted. But there's worse to come as the sun becomes more and more unstable. Violent thermal pulses of heat mean that the sun goes into overdrive. Its diameter expands 1,000-fold.
During some of these pulses, it expands out to basically the size of the Earth's orbit, and it will swallow the inner planets.
Anything in its path is vaporized. First, Mercury burns up like a giant meteor. Venus will be next. But what about Earth? Will the home that has sheltered us for millions of years suffer the fate of its neighbors? As waves of heat tear through the sun, it sheds billions and billions of tons of material into space, and its gravitational pull weakens. This may just allow the Earth to move away from the sun and escape incineration. But scientists don't know for sure, and even if Earth escapes a fiery end, it is by now an unrecognizable molten planet. It's approaching 6 p.m., dusk on our sundial, and the sun's life as a burning star is over. But it's not big enough to blow up and become a supernova. Only superstars, over 8 times as massive as our sun, explode. Eventually, it shrinks into a white dwarf, living on for hundreds of billions of years, but only producing a faint glow. So this is the way the sun ends, not with a bang, but a whimper.
The wonderful sun that provided the Earth heat and energy for billions of years will end up being a small star not much larger than the Earth.
The sun gave us life. With its death, all life on Earth will be gone. If humans still exist, we'll be somewhere among the stars. So next time you're on that beach enjoying the sun, remember, it won't last forever.
you.